So hi everyone. My name is Kevin Shah. I'm a PhD student in the CS department here at Columbia University. My advisor is Elias Barenboim, and we're part of the Causal AI lab. And today I'm going to be talking about the causal neural connection. So first, let me introduce the references that this talk will be based on. There's 3 papers. The first is the causal neural connection, expressiveness, learnability, and inference. This was joint work with Kaizan Lee, Yoshua Bengio, and Elias Barenboim. And this one introduces the idea of this connection between causal models and neural models. Then more recently, we have neural causal models for counterfactual identification and estimation. This is joint work with Yushu Pan and Elias Barenboim. And this one is an extension of the previous work that greatly generalizes all of the content and reaches over into not just causal domains, but also counterfactual quantities. And then finally, the third work isn't really related to neural models. It's on Pearl's hierarchy and the foundations of causal inference. This one is more of like it sets the foundations in causal inference about what I'm going to be talking about here today. So before we dive into the details, let's talk about a little bit about the motivation of this work. So first, neural networks are universal function approximators. So there's a well-known theorem in deep learning theory, which is the universal approximation theorem. It basically says that neural networks can approximate any function to arbitrary precision, essentially. And since most tasks in AI can be modeled using functions, then it's hypothesized that neural networks can be used to solve these tasks. And some even say maybe neural networks can solve everything. And this is further supported by the fact that neural networks have a lot of empirical success in several areas like computer vision, speech recognition, and game playing, to name a few. So the research questions that we want to investigate are, 1, how are causal and neural models related? And 2, can neural models be used to perform causal reasoning? So I'm not sure what the level of background is here for causal inference. So I thought I'd go over a little bit of causal inference review first. So in causal inference, one of the central elements, a central data structure that we use to study causal inference is called the structural causal model, or SCM for short. So this goes back to when Yuta Pearl was first studying causality. It's like kind of like the data structure that he uses, that he studies. So the SCM it represents an underlying causal system with 2 major components. There's the collection of causal mechanisms or structural functions, and this is represented with the symbol F. And there's also the external or exogenous sources of variation outside of the system, essentially like variables that we don't observe, U, and then their corresponding probability distribution, P of U. Right? And importantly, every SCM induces a structure called the Pearl Causal Hierarchy, which includes qualitatively different distributions in this containment hierarchy of 3 different layers, right? So each one contains successively richer information in some sense. So layer 1 is observational data, observational distributions. This is related to the human act of like seeing, right? So when you're passively observing the data, when you're passively observing the environment and you're collecting data, this is the kind of data you get, and this is what most data in machine learning ends up being. So this is like typically related to the machine learning tasks of, for example, supervised or unsupervised learning. For example, when you're doing classification, you're looking at maybe the association between the features X and the label Y, right? Then this is you're kind of working with observational data because you're not really thinking about whether there's a causal effect. You're just looking at any kind of like link between your features and the label. However, if we go 1 layer higher, we have the interventional layer. So this corresponds to the human concept of like doing. So like actually physically going into the system and changing something yourself, intervening, right? So you make these patients take a drug, or you implement this policy, right? Then that's like you're kind of intervening on the system, and you're changing what would have naturally been there. And these interventions result in like a more richer set of information where like maybe like experiments fall, for example. And this is often related to the machine learning concept of reinforcement learning, where you might have an agent that's like kind of roaming around the environment and actually like, while not just observing things, also kind of like changing things and seeing what happens. Right. And then finally, the third level, which is an even higher layer encompassing everything else. This is the counterfactual layer, and it has to do with the concept of imagining. So this would be like thinking. So this would be like you make a patient take the drug. The patient died, for example. Would the patient still have died had they not taken the drug? Would we still be in a recession had we not implemented this policy? Right? We're thinking about hypothetical worlds that didn't actually happen, based on what did actually happen. Right. So this is one layer above interventions because we can't just revert back time and do something else because we've already kind of committed to one course of action. Although it's very important because we're often trying to figure out what are the consequences of the action. Why did this happen? Right. What would have happened in other situations? Yeah.
I mean, also just to say that I think Pearl has collaborated with some people where you also do the counterfactual in the future, right? Like in terms of climate change, or so if we go through this emissions pathway, like so in principle, it's also relevant to the future as well, right? Hypothetical situations.
Absolutely,
yeah,
absolutely,
okay.
Yeah. There's many like motivations to why you would want to know this information, and sometimes we can't because we can't know both worlds at once. But sometimes, you know, given certain assumptions, this is something that we want to and can infer. So this is kind of the more formal definition of the structural causal model, which I'll briefly discuss. So it's the structural causal model, which we usually label with M, is a four tuple, U, V, F, and PU, right? So U is the set of background variables or exogenous variables. So these are kind of like the noisy outside factors that we don't really care about. And then V is the set of variables that are endogenous variables. These are the variables that we do care about, the ones that we observe, the ones that we are studying, right? And then the functions define the behavior of these endogenous variables in V. So each V has its own function, f of Vi, right? And then what influences that variable are its parents from the endogenous set and also certain outside factors from the exogenous set. And then finally, P of U is a distribution over the random exogenous sources of variation. So when you combine all of these, you can see how maybe you might be able to collect samples, right? Like you sample from P of U to get the exogenous sources of noise, and then you successively pass through all of these functions in topological ordering, and that provides samples for V as well, right? Then interventions have to do with replacing these functions. All right. So to talk a bit about how the PCH emerges from the SCM. So typically when we're studying something in causal inference, we understand that there is that nature has some rules and that there's some true model that's governing whatever we're seeing, but we don't typically know what it is. So we may have this SCM M star that is describing the underlying reality, but we don't see this. And instead, this SCM induces it's three layers of the PCH. It induces observations, it induces interventions, and it induces counterfactuals, right? And typically we don't know the true SCM M star. We only know data from the true SCM that comes in the form of these PCH distributions. And further, we don't always know all of the PCH either. We don't typically have counterfactual data, for example. The first question is it possible to perform inferences when both the SCM and the PCH are not fully observable? So perhaps you have only observational data and you don't have any interventional or counterfactual data, like these are unobservable, for example. And so what we want to do is we want to take our observations and we want to essentially cross layers. We want to infer something from the other layers using only the information from layer one. So that's called cross-layer inferences, and that's the other major question that we want to answer here. So what's a naive idea to try to like get started? Well, what if we just like slap on a neural model because we know that neural networks are really powerful and we try to learn it that way, right? So what we'll do is we'll take a neural model, we'll call it M hat, and we'll say, oh, okay, this neural model induces its own 3 layers of the PCH. It has its own L1, L2, L3. And what we'll do is, what we have observational data from the real SCM, we'll just train this neural model M hat so that it also matches in the true model in layer 1. And then we'll query this model. We'll check if there's anything we can learn from layer 2, right? So how would this neural model be designed? Well, let's just take an SCM, and for the functions, we'll replace them with feed-forward neural networks, for example. And then for the distribution, the noise distribution, let's just use uniform 0, 1 because it tends to be very flexible, right? So then intuition tells us that if we design the neural causal model this way, that it is very flexible and we'll be able to learn many different types of functions, right? And indeed, so we introduced the neural causal model, or the NCM. And the reason this is important, the reason why we need to use neural networks, is because we can train this model, right? It's actually, it has parameters, and we can tune those parameters to get the function that we want, right? And indeed, intuitively, it's expressive. So we show that constraining the attention to NCMs doesn't actually incur any loss of information compared to actually just studying in the space of SCMs. So just because we fitted the SCM with neural network functions doesn't make it any less expressive, essentially. And so the class of NCMs is essentially just as expressive as the class of SCMs, thanks to the neural networks, right? But unfortunately, there's also this negative result here, which we call the Neural Causal Hierarchy Theorem. And this states that despite the expressiveness of the NCM, if we only have data from a lower layer of the PCH, like observational data, we would almost never be able to make inferences about the higher layers of the PCH, like interventions or counterfactuals, using NCMs without any further assumptions. So the reason this is the case is because it turns out that the observational data highly underspecifies the model. There are many possible models which could all agree on layer 1, but they have completely different results for layer 2. And you can't just pick one and hope that it works, right? So unfortunately, our first idea doesn't work, right? But I mentioned that it's not possible without further assumptions. So what can we do with some assumptions, right? Maybe there's some sort of constraint that we can enforce directly into the neural model, something that we assume is true about the true model, and then force that into the neural model as well. We call that the causal inductive bias, right? We force the neural model to take specific constraints into consideration before attempting to fit the data. And the pipeline is like this. So you have the true model M star, then presumably it induces some sort of constraints, which now we're making some assumptions here. We're assuming that there's certain constraints about the true model that we're now going to apply to our learned model. And the specific one that we use is called the causal diagram, and it's a graph where all of the variables are nodes, and the arrows represent qualitative relationships between the variables. So in this case, here it's saying that X causes Z, or more specifically, that Z doesn't cause X, right? Here, Y doesn't cause Z, X doesn't cause Y, except through Z, right? And then this bidirected arrow is saying that there's some unobserved confounding between X and Y. And maybe more importantly, the lack of one shows that there isn't any unobserved confounding between, say, X and Z, right? So this is qualitative because unlike knowing the SCM, where we know the exact functions and probability distributions, all we need to know about this is we need to just draw an arrow and say, okay, there's some causal effect. I don't know what it is, but that's something that we think is true, right? So we know that we can't make causal inferences out of nothing. So now let's try to do it with a little bit of help, with some assumptions, essentially. We take this graph, and what we can do is we can actually force it into the neural causal model. We can force it into the construction. And for this particular graph, it may look something like this, right? Where we have a neural network for X, Z, and Y. And then the network for Z takes X as input, the network for Y takes Z as input. And then the functions for X and Y both share the same exogenous noise here, UXY. So there's two important properties that we prove about this constraint class. Right? The first is that, so we call these G-constrained NCMs, where G is the graph, right? So the first is that any G-constrained NCM is GL3 consistent. And what that means is there's a set of constraints that the graph is encoding. For example, in this graph, there's no, this one constraint is that there's no causal effect from Z to X, for example, right? There's many of these that are kind of like, there could be potentially like exponentially many different constraints. They're all nicely encoded in this graph, and all of them hold on all three layers, layer 1, layer 2, layer 3, if your NCM is G-constrained, right? So what that means is you have this dark gray area, which is the subset, or which is the space of all SCMs. And then you have this light gray area, which is just the ones that are satisfying the constraints, the assumptions that you make, essentially. And theorem 1 here is saying that there are no G-constrained NCMs that are outside of this gray circle, this light gray circle. Then the next important result is that essentially that these constraints don't hurt the expressivity of the NCM. So for any SCM that induces this graph, there exists a G-constrained NCM that is L3 consistent with respect to that SCM. So L3 consistent meaning it matches that SCM on all three layers. So what that means is within this gray circle, any SCM in there can be represented by a GNCM. So this brings us to our tasks. Now that we have these constraints, now we want to see maybe there's some tasks that we can solve, right? So the first task is causal identification. And this task asks, can we compute higher level effects like interventions or counterfactuals from lower level data? It's like a yes or no question, right? Like basically we have this query we want. Maybe it's a causal query, maybe it's a counterfactual query, but all we have is observational data. And we want to know, can we actually get this? Can we actually answer this? Right. And the fact or the goal of answering that question is a task in itself. So there's extensive literature in this problem under various assumptions in terms of input and output. And one well-known one is Pearl's do calculus. Right. So this has essentially been solved in many different problem settings symbolically, as in people have figured out how to use math and like tweak around the constraints, looking just at the graph to solve this question. But there's currently no neural or optimization method capable of solving this method, or like not until this work at least. And then the second one is causal estimation, where, okay, we've determined that the query is identifiable, as in it can be computed. How do we actually do it with finite samples and computational resources, right? And actually, for like causal queries in L2, which are identifiable through adjustment, which is this common assumption that you might see in the literature. It's also known as the backdoor condition or Rubin's ignorability conditions. There's actually extensive literature on how to estimate those cases using both neural and non-neural methods. So these are, this is like one specific set of assumptions, which is made frequently throughout the causal inference literature. This has been very well studied. On the other hand, that set doesn't represent the case of, or the set of all queries that are identifiable. So for other effects that are identifiable, the options are a lot more limited. And there are methods currently that are based on machine learning or robust statistics, but there's no neural method for performing estimation in general, which is one of our biggest motivations, because since we believe that, since we've seen the strong successes of neural networks, we would like to use the strength to improve our performance at estimation. Yeah.
What methods do you mean? Yeah, there are methods based on machine learning.
Yeah.
Do you
So
know names.
Yeah. There's one approach called weighted empirical risk minimization.
Okay. Yeah. I know this.
Yeah. Okay. Yeah. Yeah. That's one of them. And then there's also these ideas like there's one called double machine learning.
Yes. I
Yeah.
know.
Yeah. So So these are some approaches that you can use, and they've actually these have been extended more generally past the backdoor and can be used in a wide variety of settings.
Sorry, basic question from very non-expert. What do you mean by identifiable?
So basically, it's identifiable if we know that we can, if it's like a higher level quantity, a higher layer quantity, and we know we can compute it from the lower layer data, right? And then I'll go into more detail about about how this problem is solved like later in the presentation. So hopefully it'll be more intuitive. Okay. Yeah. So I guess right now. Yeah. So the this is the before we talk about identification in the context of NCMs, let me first discuss what the classical identification problem is. So it's the very first instance of the identification problem. What is it really saying, right? So this is just causal effect identification all the way back from Pearl's textbook, right? The definition is you're given a causal diagram G and the observational distribution PV. And then we say that the causal effect P of Y given do X, so this is the causal effect of X on Y, is identifiable from the observational distribution PV and the graph G, if and only if for every pair of SCMs that induce the graph G, if they match in the observational data PV, then they also must match in the causal effect of X on Y, right? So the diagram here kind of shows what's going on. We're saying it's identifiable if you can take any pair of SCMs such that they match in the observational data and in the graph, and they must also match in the query, the causal effect of X on Y, right? So what this is saying is, okay, if we can take any of these SCMs, we can just make sure that they match the constraints in this graph, and then we make sure that they induce this observational data. Then we're guaranteed that they can give us the correct query. And even if it's not the true SCM, right? As long as it satisfies this, this is called identifiable. Right? Here's kind of a visual explanation of how this works. So let's say here that this gray circle, this dark gray circle, is the space of all SCMs, omega star, right? And each dot is an SCM. We have this unobserved truth, this true SCM, M star, which is this green dot, right? And then this light gray space is the subspace of all SCMs such that it matches M star in the observational data PV and in the graph G, right? So it matches P star, V, and G star. Then what we're saying in the definition of identification, if it's identifiable, you can take any of these two SCMs in this light gray space, and they will match in the causal effect of X on Y, right? On the other hand, in the non-identifiable case, you'll have the same thing. You have the observational, you have the true SCM M star, and then you have the space of SCMs that match P star, V, and G star. But you can find two SCMs where they won't match in the causal effect, despite matching in both observational data and graph. So how does this kind of translate to when we're working with NCMs, right? So the definition changes like this. So now consider the true SCM M star and its causal diagram G and observational data PV, right? Then the causal effect of X on Y is said to be neural identifiable from the set of G-constrained NCMs, which we label as omega G, and observational distribution PV, if and only if for every pair of NCMs that are G-constrained, we have that both of them match the true model in observational data. Then they must also match in the causal effect of X on Y, right? So here Yeah, so the diagram here on the right, here we're showing that we have the space of NCMs in blue, and that's actually a subset of the space of SCM, right? And the true SCM M star doesn't have to be an NCM, it can be anywhere. But we're saying that it's neural identifiable as long as you can take any two NCMs that match in the observational data and the graph, and then show that they must also match in the causal effect of X on Y. So in the graph, it would be something like this, where now we're looking at a smaller space. We're looking at just this blue space. Right? This blue space represents the set of SCMs that are NCMs. And now we're trying to see if any pair of NCMs, as in this intersection between the blue circle and the light gray circle, we want to see if any pair of those match in P of Y given UX. And in the non-identifiable case, we can show that there's two NCMs that don't match. Right? So this was kind of like the most basic type of identification, just to kind of give like an overview of like how it works. But more generally, we in the newer work, we have this much more general definition of identification, where now instead of just P of V, we could have any arbitrary set of data sets from L1 or L2, right? So maybe you have observational data, but you might have also done some experiments, right? You have interventional data on this variable, but maybe not this one. And then you can have like some arbitrary set of experiments that's described in this data set Z. And then you have a counterfactual query Q. And since counterfactual is the third layer, it encompasses layers 2 and 1 as well. So it's written in this form, but don't worry about that too much. Basically, just think of Q as any query from any of the 3 layers, right? So you're interested in some query, right? And then we say that it's neural identifiable from omega G, the set of G constrained NCMs, and this data set Z, or this collection of data sets Z. If for every pair of SCMs that match in the data and in G, if for every pair of NCMs, they also match in the query. Right. So the diagram is similar, but rather than just one data set, like in the observational data, we have all of the data sets in Z. And for the query, it can be any arbitrary query, not just necessarily the causal effect of X on Y. It can be any query from L2, L3, any query that you're interested in answering. So one thing that's a little bit weird about the neural identification definition is, well, if we're working just in the space of NCMs and the true SCM is not an NCM, right? Why do we care if all of the NCMs match in the query? How does that, what does that mean about like the true model, right? How does that even relate to like the regular definition of identification? And it turns out actually that they're equivalent. So despite the fact that we're searching in the space of NCMs, it turns out that if we can conclude that it's identifiable in the space of NCMs, we can also conclude that it's identifiable in the space of SCMs. So this is the theorem. This is what we call the dual ID theorem. It's saying that if Q is neural identifiable from the space of NCMs, omega G and Z, then it's identifiable from just G and Z, like classically identifiable, and also vice versa. So this is an if and only if statement. So that allows us to actually solve the identification problem using an algorithm like this. So what we'll do is first, we'll create 2 parameterizations of the neural causal model. First of all, this just to reiterate, this NCM is constrained with G, right? And then what we'll do is we'll create 2 sets of parameters for it, or you can also think of it as creating 2 NCMs, right? Such that one of them is trying to maximize the query, the other one's trying to minimize the query, and they're both trying to fit the data set.
Kevin, can you remind us what you really mean when you say the NCM is G constrained?
Yeah. So we had the graph, right? Which that's an assumption. that we make out of necessity because we can't make inferences otherwise. And what we're doing is we're straight up like enforcing that graph into the construction of our NCM, right? When the functions are literally like created this way to fit the graph, it's very much constrained, right? So it satisfies all of the constraints as we proved as well. Yeah.
Thank you.
Yeah, so what we're doing here is we're creating two parameterizations, one that's maximizing, one that's minimizing the query.
Sorry, could you just maybe give an intuition for what does maximize or minimize in the query mean?
Yeah, so let's say that we want to see the causal effect of taking this drug on the recovery rate of a disease, right? Maybe if they didn't take the drug, their recovery rate would be 0.6 or like 60%. And if they took the drug, the recovery rate is 80%, right? Now, we want to know the causal effect of giving the drug. We want to know this 80% number, right? So what we'll do is we want to know if it's identifiable, right? Like if we just like train some model and it spat out 80%, we don't know if we can trust that number, right? What if it could be anything and it just happened to give like 80%, right? So what we'll do is one of the models will try to make the number as high as possible while still being constrained by the graph and also still fitting the data set, right? And the other one will try to make it as small as possible while doing those same things. So what will happen is if they both give 80%, what that means is they tried as hard as they could to make it not 80% and it still ended up 80%, which means you can trust the number. Otherwise, one of them will be like maybe 90% and the other one will be like 50%. And then you'll know that, okay, it's probably not 80% because it could be like pretty much anything in between those two ranges, right? So that's what we're trying to do here. So yeah.
You do that in practice.
Yeah. So this there's two approaches. One, the first one we tried was with the maximum likelihood estimation approach. So I do have a slide on this. I actually removed it from the presentation because I thought it would take too long to explain, but we could get to that like at the end if there's time. But to like kind of explain it briefly, there's like one approach that's maximum likelihood estimation. You're essentially maximizing the likelihood of the data sets while simultaneously trying to maximize or minimize the likelihood of the query, right? And the other one, like that's done using some sort of gradient descent optimization approach with a loss term that has like kind of both, right? So it like adds the two losses together. The second approach, which is more recent, it's like less accurate on smaller scales, but like a lot more tractable at larger scales. It's using like a generative adversarial approach. So this is more of an implicit approach. You're not really modeling the likelihood of the query or the data set. You're actually just implicitly modeling it through samples, right? And then you can essentially, if you're familiar with GANs, that's how you can train to fit the data sets. And then there's another term that penalizes or rewards the value of the query, essentially. So those are kind of like the two approaches that we use in practice. But we can go over to the slide with more details at the end if there's time. So yeah, it's a good question though, because this formulation of the algorithm is just to kind of like explain intuitively what we're trying to do, not actually show how it's done, right? So here we're trying to maximize and minimize it while satisfying these constraints. Then we're going to check if they give the same result, and if they give the same result, then they match. Or sorry, if they give the same result, then it's identifiable. If they don't, then it's not identifiable, right? In practice, they're not going to exactly match ever. So we do some hypothesis testing and check to see if it's under some threshold. And then finally, if it is identifiable, we can actually just directly compute that value from either of the models, right? And then the effect, like if you the nice thing about this is that when you query a causal effect or a counterfactual from an SCM, it's already well defined. So then you can just directly compute it from this NCM. You don't have to do any kind of fancy like curve fitting or anything. It's already there, right?
Kevin, just a minor question. Do we know a priori the such that condition where m hat is what you're optimizing for and m star is the true distribution?
So it's kind of like in practice. Sorry. Are you saying like
I mean, these are the optimization conditions, right?
Yeah.
But do we know anything about M star?
Yeah. So Z is the data sets that you're given.
Right.
Right. So the in theory, I guess, when you're given Z, they come from the real SCM, right? And then these are certain distributions that you actually have from the real SCM. These might be certain observational or interventional distributions, right. But you probably don't have everything, right? But this is what you at least do have, right? So of course, if you're given something, you want to at least make sure you match what you're given. And then everything else, you have to use the identification algorithm to see if you can infer that.
Yeah, maybe because in my mind, it was always like 2 layers of at least 1 degree of separation between M star and what you're given. But you're just saying what you're given is you can treat that as M star.
Exactly. Yeah. Well, so like you don't have the whole M star, and you don't have even every distribution of M star either. You just have certain data sets that's represented in Z. Yeah. So when the notation I'm using here, when I say Z of M star, I'm saying the distributions of Z that came from M star versus the distributions of Z that come from our NCM M hat. Yeah, so this algorithm that we just discussed, in theory, is both sound and complete. So what that means is if we run the algorithm and we get our result Q hat, then it turns out that Q is identifiable from G and Z if and only if Q hat is not fail. Moreover, if it's not fail, then that value is equal to the true value, Q star. Okay. Yeah.
I just ask maybe a naive question. If your query is not identifiable, does this process, do the bounds you get out of your neural models give you real bounds on your query, or is it just meaningless?
That's a good question. Theoretically, yes, actually. So if it's not identifiable, then the results can be interpreted as bounds on the causal effect. But in practice, we've had a hard time getting accurate bounds. So we didn't include that as a result in the paper. But theoretically, yes, you can treat it as bounds. Yeah, it's very, very ripe, open research direction. Yeah, so I guess at this point, all that's left to talk about is experiments. I'm not sure if anyone still has any questions about like the theoretical content.
I had a question.
Oh yeah.
Like, do you have to worry about how long this would take to, I don't know if converge is the right word, but like to not fail, basically, depending on like how complex the.
You mean, are you talking about like to get the identification result or to get accurate estimation?
Yeah, to get the identification result.
So maybe this will be more evident in the experiments, but okay. Generally speaking, the longer you run, the more confident you can be in the results, right? Mm. But certain results you can be confident without running that long as well, right? So I guess it's kind of up to you. If you want to have more faith in your results, you can just try to run it for longer. But we'll show that. So we do these experiments in a very small amount of epochs, like maybe 1,000-ish. Which doesn't take that long in practice. So even like maybe like a small amount that you could run on your laptop, you can reasonably expect good results, I guess. And also this depends on your implementation in practice, of course, because there's different ideas on how you might want to implement this, and I guess it's in some ways it's more of an art rather than a science. But here's like essentially like what we're doing with identification, right? So on the left here we have 4 identifiable cases. This is specifically just the causal effect of X on Y from observational data. On the left here, there's 4 identifiable cases where the causal effect of X on Y is identifiable, And on the right, there's for non-identifiable cases where the causal effect of X on Y is not identifiable from just observational data. And so we analyze what happens when we run the algorithm on these 8 cases. So what happens is, I guess maybe the bottom graph is more interesting initially. So the bottom graph, we ran everything several times, and the bottom graph shows kind of like the distribution, the percentiles of these gaps, right? The difference between the maximized and the minimized result, right? And what happens is we kind of like we enforce the penalty on not fitting the data as we progress through training. And what happens is in the identifiable cases, you can see in the bottom row that the gaps move to nothing in the identifiable cases. But then in the non-identifiable cases, they tend to stay pretty large, right? So what's going on here is like if you see even like the largest gaps between the maximized causal effect and the minimized causal effect is very, very small. So they kind of match. But in the non-identifiable cases, some of them, like this first graph, for example, like all of them agree that the gap should be really, really big, right? And there's some variation in this result, but some of that is also because of when we're working with different true models, sometimes the gaps the true gap can vary, like the true bounds. And then of course this top row then is converting this bottom row, the results in the bottom row, to an actual ID result, like a yes or no, based on our hypothesis testing procedure. So we have 3 thresholds here. Blue is 0.01, green is 0.03, and red is 0.05. And then you can adjust tau based on your experimental like needs, I guess. Where if you choose a lower value, then you'll end up with more false negatives. And then if you choose a higher value, you'll end up with more false positives. And then for estimation, we took the 4 identifiable cases. Yeah.
Before you move on, can you just, like, for somebody who doesn't do this very much, explain how the graphs, or like, how do you know what's an identifiable case or non-identifiable in this? Like, you built those experiments, right?
Mm-hmm.
How did you make something identifiable?
Well, like, how did I know they were identifiable in the first place? So these are well-known graphs in the literature, and for this particular setting, you can actually use do calculus to derive the fact that these are identifiable. And then there's also proofs that show that these non-identifiable cases are non-identifiable. But this is like a very limited setting in which it's the specific case where you have observational data and you're trying to get the causal effect of X on Y. And it's these specific graphs, I guess. Yeah. There's certain tasks or there's certain identification settings, like for example, the one where you're given the graph and observational data and you're trying to get the causal effect of X and Y. There's certain cases where it is actually solved like in generality, symbolically, like using math, basically. So you could design an algorithm that doesn't have to go through all of this and get the result that way. But this is providing like a very flexible approach that solves any kind of general problem setting that might be kind of related to the identification problem, or like different versions of the identification problem that aren't just like the classical identification. Also, it's philosophically, it's kind of neat that it's the neural network itself that's actually doing the causal inference in some sense. Like here, you didn't have to know that it was identifiable or non-identifiable, but you can tell just by looking at the graphs, because like these cases, it's like the gaps are so small, but over there the gaps are so large, right? So that's kind of like the neat part that the experiment's trying to show.
There's a question online.
Yeah, what's up?
I don't know if this is a dumb question, but like as far as for the experiments, like are there any assumptions that go into the observations? Like do they have to all be independent or just that?
Like the input data sets?
Yeah.
I guess we do assume IID.
Okay.
So in the theory, we actually assume that we have enough data such that we know the actual distribution. Like we kind of, so maybe we have observational data from the distribution PB. We assume that we have enough data that we can just assume that we have PB, basically, right? Like the actual distribution over B. In practice, that's probably not going to be the case. Because we have limited data, the empirical distribution is probably not going to actually be equal to PV. And so the results here are limited to the how well the empirical data matches the true data or the true distribution. That is a limitation. I think it would be interesting to see some kind of like error analysis, but for now, the interpretation is that your result is only going to be as good as your data is. Does that answer the question?
Yeah, I think so. I guess I was just curious, like, how do you actually generate the data here? Like, are you creating functions? Yeah, I guess I don't know if you have time to go into more details about that, but
that's like, these are simulations, right? And then yeah, so yeah, we randomly generate some SCMs, and then we sample the data IID, and then that's how we get the experiments.
Okay, cool.
So once you conclude that the result is identifiable, you can then try to estimate it, right? So these are the estimation results. We show like the error plotted against like having more samples. The top row shows how well we're able to match the given data sets. So we plot KL divergence here with PB, and then the bottom row shows how well we're able to estimate the query. This is the error over our query, which is the causal effect of X on Y. Here we're comparing 3 models. Orange is our method with the NCM. Blue is a naive model where you're kind of training a neural network to fit the data without the graph and seeing if it'll give the right causal effect. And then green is weighted empirical risk minimization, which is another technique that's not really related to fitting an SCM. That's also used for estimation, right? So when it comes to fitting the data, which Worm doesn't need to do, both the naive model and the NCM are capable of fitting the data, right? So as we get more samples, we reduce the KL divergence data, and both models are good at doing that. But when it comes to estimating the query, you can see that with more samples, the NCM is able to improve its estimation, whereas the naive model is basically not learning anything, except in this third case where conveniently the causal effect happens to also be the association between the two models, right? So in this third case, the causal effect of X on Y is actually just equal to P of Y given X. Then in that case, it is giving the right result, but of course the NCM can give the right result as well. And then Worm, which is an entirely different estimation method and part of like one of the state-of-the-art methods in some sense. It gives comparable or even worse results sometimes.
So POV is the joint distribution of
your variables. This is like the observational data across all of your variables. Yeah. I mentioned earlier there's kind of 2 approaches to that we've tried. The first one was the maximum likelihood approach, and the second one, which is like the more implicit method, is with the GANs, right? And the reason we introduced the GAN NCM is because even though the maximum likelihood approach is like theoretically the best at lower dimensions, it just scales really badly. And here we show that when you increase the dimensionality of the data, the MLE NCM grows, like the runtime grows exponentially. But then with GANs, you can pretty much still get the same runtime, same performance. So that's why we pivoted later on. And so basically the GAN NCM allows greater tractability at the expense of slightly higher estimation error at lower dimensions. So now here's an experiment showing comparing the 2 types of NCMs, but for counterfactual identification. So these are the accuracies for performing identification in these, there's a lot of settings here. Each of these graphs represents a different setting. The graph on the left shows what graph is being used. The query at the top is the query that we're interested in. So there's four different queries here. AT is just the causal effect. ETT is a counterfactual effect of the treatment on the treated. Yeah, that's what it's called. And NDE, natural direct effect, that's also a counterfactual quantity. And then CTFDE, or counterfactual direct effect, that's also a counterfactual quantity. So each of these has like kind of implications in fairness analysis. They're kind of well-known queries. That's why we wanted to test on those. And then for each of these queries, there's two columns. One is with just the observational data, and the other one is with the observational data and also with experimental data on X. The blue backgrounds show the ID cases, and then the orange backgrounds or the yellow backgrounds show the non-ID cases. So here we're comparing the GAN NCM with the MLE NCM, the two approaches from before. The MLE NCM it actually tends to have like sharper performance for identifiable cases, but for non-identifiable cases, it sometimes mistakenly classifies it as ID, which is kind of dangerous actually, because if it's not identifiable, you really don't want it to be ID. And if it's ID, but you accidentally say it's not ID, then that's okay. Like that, you're kind of just cleaning on the safer side. Right? So the GAN NCM does a better job of balancing both cases. And then moreover, here we also show the GAN NCM with a 16-dimensional case, which the MLE NCM just straight up can't do. So that's one additional result that we have here. And then there were 16 identifiable cases here. And then here we're showing the estimation error as well, comparing between the two models. So in some cases, the MLE NCM is better, but the GAN NCM does pretty well, and it can also work in 16 dimensions. So that's kind of like the benefit over the MLE NCM. So I believe, yeah, so that's everything for experiments. Does anyone have any questions on experiments? Okay. So to conclude, right? The first takeaway is that cross-layer inferences are provably impossible without assumptions, even if you're using something as expressive as as a neural network. But a graphical inductive bias can allow neural models to solve the causal identification and estimation tasks. So when you have this graph, for example, and you like impose it into the NCM, you can then perhaps get some of these results that you can maybe do some inferences across layers. The causal diagram is not the only type of assumption that can be made. And looking at different assumptions, that's an avenue of future work as well. With some without assumptions, we can't get anything. So it's interesting to see what kinds of assumptions can lead to something and what kinds of results they can lead to. What's cool about this work, I guess, is that for the first time, neural networks have performed like causal reasoning in some sense. Like neural networks are pretty good at fitting functions and fitting like once you already have the function that you want to fit or the query that you're trying to answer, you can use a neural network to fit that. But in this case, we're actually using neural networks to actually see, hey, is this query causal? Right? And so in that sense, the neural networks have actually done the causal reasoning themselves. That's one aspect of this work that I feel is cool. And we hope that this work shows the foundational connection between causal neural models, and it'll pave the way for a rich symbiosis between these modes of reasoning, which will lead to more robust and scalable causal inferences through neural technology.
Thank you.
I guess before, do we have time to like pull up the other slide? I guess.
Yeah, I think since you're in the room, maybe we can open the floor for online questions and just continue the conversation. I mean,
we can. Yeah, sure. Let's do questions first.
Right. Is that okay?
Yeah.
Good. Okay, Kara, you have a question.
Okay. I was curious, like, do you think there's a way to connect this eventually to things like equation discovery using neural networks, or is that, I don't know if that's at all in your line of thinking?
Can you define to me what that is? I'm not familiar.
Oh, I mean, like directly, like trying to determine what the neural network is, learning in terms of like a functional model for say a physical system.
You mean like actually finding the true functions?
Yeah, exactly.
Yeah. So yeah, that's an interesting point. So in this work, we're learning to fit the data, but we don't actually care what the actual functions are. We're just like saying, oh, okay, learn whatever parameterization is necessary to fit the data, right? Then if we could get the actual functions, that might be more interesting because then we would learn something that's kind of fundamental about nature in some sense, right? And I think like maybe it's possible, but there's always going to be like a few barriers. So one is that like if we don't know the exogenous sources of noise, like if we don't really have a full understanding of the whole system, then it's always going to be hard because there's going to be some sort of outside factor that's affecting those functions that we don't know about, right? And then the second issue is that learning the function is just so much of a stricter requirement than identifying just like a causal query. So you may end up with a lot of negative results, which would suck, I guess. But it certainly would be interesting, and I think there might be problem settings in which it could be possible.
Thank you.
Any other questions?
Yeah, I don't see any other questions online.
Okay, sounds good.
Oh,
I was just going to ask that, beyond the experiments that you showed, has this been tried in some real world applications with like, some real world data so far, or is that future work?
I think like nothing published, but it would be interesting to see. I guess the difficulty is that there's not a lot of like well-known causal data sets that isn't like for example just with the backdoor conditions, for example. So it's kind of difficult to have like to have real world experiments in a paper, for example. But certainly like it'd be interesting to see like what kinds of applications are possible like in industry, for example.
What are the backdoor conditions? Sorry.
Yeah, so there's actually, maybe I can highlight that here. So you see this graph here. So this graph is known as the backdoor graph, and it comes with a set of assumptions, which are actually very commonly made. So a lot of papers, they actually just make, they don't assume they have a graph, they just directly make the assumptions that this graph has. Right? That proportion of literature is like a very big chunk of like the causal inference literature. Because it's so widespread, like there's a lot of techniques out there that solve the problem under those assumptions, and then they, of course, there's a few data sets as well, but because like our approach works with a lot of different settings, we didn't want to just test on like just like a backdoor setting, for example. Any other questions?
Oh, I was just wondering, like, this is all conditioned on knowing information about your endogenous variables. Do you also need to know information about like those exogenous variables, or?
So actually that's kind of like a neat part of this work. It's like I guess in general you don't care about those variables, right? So but like when you're defining the when you're thinking about it semantically in terms of like the true SCM, they are going to be well defined, and they are going to have like certain forms, certain properties, right? The nice thing here is that we just use uniform 0, 1. Like we don't care what the exogenous variables are. We just use uniform 0, 1 random variables. pass that in as input, and then it can kind of like mold that distribution to whatever it needs to be to fit the data essentially.
Do you need to maintain the same distribution of those exogenous variables in order to like make inference?
Yeah. So we don't know the true distribution of the exogenous variables, but if we manage to fit the data successfully, I mean, it'll do its own interpretation of it'll kind of like change that exogenous noise into one of its own distributions, like through the functions that it learns. And then as long as that distribution, that final result fits the data and you find that it's identifiable, the neat part is it didn't really matter what the true exogenous noise was or what the true functions were. You can still get the correct result.
Okay, and then that's what makes it difficult to then extract it.
Exactly. Yeah. So if you had to know the real noise or like the real functions, that would make it a lot more difficult. But this is also something that is commonly an assumption. Like we don't make this assumption, but like a lot of papers they'll assume that maybe it's additive noise, right? Like noise is all Gaussian, and then you add that, like the function is defined such that you take the endogenous parents, and then you just add some like Gaussians, and then.
But in the real world.
Yeah, but we don't make that assumption because it could be anything really, right? So yeah. All right, I think I guess time's up, right?
I mean, but for the folks online, we can thank them, but we can continue. Like I don't know. I mean, it's up to you. Like
I felt like I was worried I was maybe going over or something, but
yeah. I should also say that we're going out for lunch after this with Kevin.
Yeah.
So feel free to join as well.